Thank you, Tom. Hello, my name is Don. I'm a developer advocate. I work at Google, and it's my job to help developers bring their apps to Android. That mostly means listening to sine waves, square waves, solving latency problems, and problems with computational throughput. So I'm going to talk to you today about how you can bring your apps to Android, get the best performance and best latency across the widest range of devices. So, who's this talk for? People who like square waves. So there'll be a lot of square waves. Last year was the year of the sine waves. This year is the year of the square waves. So, also developers targeting Android or thinking of targeting Android. And that means if you're building your own audio engine or if you're using JUCE. I'll cover kind of both those use cases. Okay, so really who we're talking to are people developing rhythm games where you are tapping in response to some rhythmic event, DJing, scratching, and kind of real-time audio effects types of apps. Karaoke is a big use case at the moment on mobile, but also like guitar effects where you're processing the microphone input in real time. Virtual reality is also a big industry at the moment where you have objects in a virtual space which are producing sound, and that sound changes in response to the position of your head, and it must change in real time, otherwise it warps the reality. And then of course there's a whole suite of apps for doing musical performance, synthesis, live looping, all that kind of stuff. So if you're developing any of these kind of apps, then I want to help you get the best performance on Android. So I'm going to cover building an audio engine from scratch, using JUCE to target Android, and also how you can debug, profile, and optimize your apps. But before I do, I wanted to give a quick update on the state of Android audio latency in the device ecosystem. So typically, I come here and I say, hey, Google's been working really, really hard on bringing the latency of their devices down. So the last, every single Pixel device has great audio latency. But the response that I get from developers is, we don't care about Pixel devices because no one's got them. What we care about is the market leaders, Samsung. And I'm very pleased to announce that Samsung, the two flagship devices, have very close to 20 millisecond round-trip audio latency. So now we have a large number of devices in market with great audio latency. So I'm going to show you how to build an audio engine on Android. And to do it, I'm going to use a library called Oboe, which was in developer preview a long time ago, but recently in the last few weeks, went into production. It's an open source library available on GitHub, and we just hit 1,000 stars, so yay. So Oboe is a C++ library which is designed for high performance and low latency, and the way that it works is it uses the low-level C API A-audio on API 27 and above. And that gives you the best possible performance. And if you're running on a device which is not API 27 or above, it falls back to OpenSLES using, which is available from API 16 or above. So it gives you the best performance on the widest range of devices, about 99.5% coverage. So rather than me talk about how to use Oboe, I'm actually going to show you how to use Oboe. So I'm going to build a musical instrument, probably the world's worst sounding musical instrument, and I'll try and build it live. So this has worked about 50% of the time in rehearsal. That was until my MacBook broke on Sunday, and this is a brand new MacBook, so who knows what's going to happen. So before I get started, I'll just explain the architecture of this app. So we have an app, and inside it, we have an audio engine. That audio engine is going to create an audio stream, and that's provided by this Oboe library. And the audio stream is responsible for putting data out to the speaker or the 3.5mm jack on this Pixel XL device, which I have here. Every time the audio stream needs more data, it's going to send us a callback. and then our audio engine is going to put audio frames of data into that audio stream, and we get this callback loop for a continuous audio stream. We're going to have some control using tap events. So when I tap on the screen, produce a sound. When I lift off the screen, we'll stop the sound. OK, here we go. So I have Android Studio running here, and I have a kind of very basic template app. Now I'm just going to, there's just a few things in here which enable me to do this in the time. So I'm just going to run this app so you can see, there's no smoke and mirrors. This is kind of genuinely live. So I have an app here, and I'm tapping on the screen, and nothing's happening. OK, just so you know. So, I am in Android Studio. I have my main activity, which is what you have with every Android app. And when the app starts, it's going to call this onCreate method. Now, because Oboe is a C++ library, I need to move from Java into C++ using JNI. So I've set up a few kind of placeholder methods here. And the first one is start engine, which is going to be used to start our audio engine. So I'll call that and go into this method. OK, so now I've opened up my JNI file, which is called nativelib.cpp. And now I'm going to define my audio engine. So let's just define this here, audio engine. And I'll call it engine. And then I'm just going to call engine.start. OK, now I've already put placeholders here for the header and implementation for my audio engine. I just need to implement them. So let's define a class, audio engine, and define a public method, start. And then I can just do option enter to generate the definition for the start method. To use the Oboe library, I need to include the Oboe header. So I just do include, oops, let's get rid of that, Oboe. I've already set up Oboe to be included in this project. And to make it easier on my hands, I'm going to use the Oboe namespace as well. So, right. So now I can start using the Oboe library. So I need to build a stream. And to do that, I use an audio stream builder. And the builder allows me to set properties on that stream. So I'm going to set the format. So let's do audio format. So this can be floats or 16-bit integers. I'm going to use floats. I can also set the channel count. I'll just do 1 for mono. If I wanted a stereo stream, that would obviously be 2. So my, my audio stream builder allows me to also specify what I want the stream to do in terms of its performance requirements. So I can use this thing called set performance mode. And there's a few performance modes available to me. Low latency, none, and power saving. Because this is a real-time app, I want to use the low latency setting. And there's one final thing that I can do to create a low latency stream, which is set the sharing mode. So there's 2 modes here, either exclusive or shared. Now the default is shared, which means that my audio stream will be shared with all other audio sources on the system. So all apps, all their audio sources get mixed together, and then it gets pushed out of the audio hardware. If I request an exclusive stream, and the device supports it, then I can cut out this mixing buffer and shave a few milliseconds off my output latency latencycycycycy So that's what it. Yeah, sure.
Let's say that I Let's say that I change this mode in runtime. What happens?
So the question is, what happens if you change the sharing mode at runtime? Once you have opened the stream, you cannot change the mode. So you would have to stop the stream and reopen the stream with a different mode. Also, since we're talking about it, there's no guarantees that you would get an exclusive stream because it relies on the audio device, the actual audio codec, supporting at least 4 channels, because you always need 2 channels for all of the system sounds and all the other apps, and then optionally you can have another 2 which would give you a single exclusive stream. So, and if another foreground app comes in and you're backgrounded, you might lose your exclusive stream and your stream might be restarted in shared mode, and then it would be mixed with all the other sounds on the system. So I've done everything I need to do to open a stream, so I just call open stream, and that takes a reference to, not that object, a stream, okay. It's in red, and I can use Android Studio's autocomplete to create a new field. So it's created me an audio stream object here. And the final thing I need to do now that I've opened my stream is set the buffer size on that stream. So I can do that by doing set buffer size in frames. The smallest possible buffer size is determined by the audio device. And audio devices read data in chunks, and we call these chunk sizes a burst. So I can obtain this burst size by doing stream get frames per burst. And that gives me the smallest possible buffer size I can use in my audio stream. This is actually a really bad idea, and I'll explain why later, but don't do this. Okay, so once I've set everything up, I can now start the stream, and this creates me a pipeline from my app to the audio hardware. But nothing's going to happen now because I haven't put any data into the stream. So how do I get data into a stream? Well, if you remember from the architecture diagram, we use a callback. So I can use my builder to set a callback, and that is going to take an, I don't know if you can see that, an audio stream callback object. So what I'm going to do is just have my audio engine implement this, this object interface, and to do that I'll just go back into the header, stream callback. Okay, and again I can use Android Studio's autocomplete to do Control O, and it shows me the methods which it's able to override. The one that I want is on audio ready. And this is the method which will be called every time my stream needs more data. We have 3 arguments. The stream, which needs the data, the audio data itself, and the number of frames of audio data. Now, this is the most important one here. This is a container array, and it's of type void star because it can be either floating point or 16-bit integers. So it's up to us to cast that container array back to the type which we're going to be supplying our audio frames in. So now I need something which is going to produce a sound, and luckily I've prepared an oscillator. So I'm going to cheat a little bit here, and I've prepared an oscillator which is just a square wave. So I'm going to call this method render audio. It takes this container array, and it's just literally going to populate every element in this array with a value which is either negative amplitude or positive amplitude in order to create a square wave. So we need to define an oscillator, and it's a template type, so I just need to tell it what the audio format is. I'll include the oscillator header, and now I can go back into my implementation and just do osc render. I need to cast the audio data array back to an array of floats. And I just tell it the number of frames that we need to render. The last thing I need to do in my callback is return from it, and it requires that I return a data callback result, so that can be either continue, which will mean the callbacks continue, or a stop, which will stop them. So I'm going to continue. Right, we're almost there. I need to set up my oscillator. So I'm going to set a frequency of 80 Hertz. I'm going to set an amplitude of 0.3. I'll set the sample rate, which is dependent on the audio hardware. And so I set the sample rate and I obtain it from the stream. The last thing I need to do is have some form of control. So go back into Java land here, and all I need to do is override the touch event handler. So every time I tap on the screen, a touch event will be supplied to my activity. If I want to capture that event, I override the on touch event method. And all I'm going to do here is say, if the event is not that motion is down, then I'm going to call this native method and say that we are tapping down. And if the event is up, then I'll say tap false. Okay, so let's just implement this method. Android Studio's got the method signature slightly wrong, so I'm just going to redefine it. So I'm back in my audio engine implementation, and all I need to do here is do os set wave on, and I pass in this value here. Okay, I think that's everything. I'll run it, see what happens. Okay. So what should happen is, when I tap on the screen, we hear an 80 Hertz square wave. There we go. So that's about the most basic possible audio engine you can write in Android. Hopefully you've seen it, it's fairly simple, and it also gives you the lowest possible latency. So on a recent device, we have a very responsive touchscreen, and the audio latency is probably, well, the output latency is about 15 milliseconds. Tap to output, probably in the region of 40 to 50 milliseconds. So it's very responsive, which is cool. So that's how you do it in straight C++ using Oboe. Now let's go to a JUCE project, which is running on desktop. So, and I'll show you how to add Oboe support to a JUCE project. In fact, so that you can have Android as a publishing target. Okay, so here I have the producer. So how many of you use JUCE? Just so I know. Okay, so a fair amount. So I'm using the producer here. Now, one thing to note is that I'm using the very latest version of Producer, and it's actually on the develop branch. So if you want to target Android, I highly recommend using the develop branch, because in typical style, when I knew that I was doing this talk and I wanted to talk about JUCE, this is about 2 weeks ago, I started writing a whole load of code and trying to port a JUCE app over to run on Android, and I found a load of bugs. And me and the fantastic engineers at Rowley have fixed a load of bugs and done a whole load of updates over the past couple of weeks. So yeah, use the develop branch and just rebuild the producer. So to add Android as a target, first go into this exporters section, hit add, choose Android. Okay, now to add Oboe support, you'll need to clone the Oboe repository, go down here and put the path to the repository in here. So I'll just grab this. So that's going to be here. So I've already cloned this to my local machine here. So I'll just grab the path, paste this in here. Now I need to go into modules, audio devices, and I need to enable Oboe here. And there's one final step, which is, I mean, this will build and run, straight out of the box, which is really good. But the build time is rather long. So what I tend to do is on my debug build for Android, I will specify in this architectures text box the architecture of the test device that I'm running on. So in my case, that would be ARM64 V8A. If you're running on the emulator, it's going to be an x86 architecture. And that just speeds up your build times. So now if I select Android as my exporter, hit save, it's going to open Android Studio. I've just realized I haven't shown you the project running on desktop, which is kind of the whole point. So here's my project running in Xcode, and if I just hit run, it's a very similar app. So when I tap on the screen now, you should hear the same square wave. A lot louder, sorry. So now all we're going to do is deploy the same app onto Android. So when you first go from the producer into Android, you're going to be prompted with this import project dialog. So we'll just hit OK there. And we'll wait for Android Studio to index some of the files, but we should have a run configuration here. Okay. Right. I'm sensing a problem. Hang on a sec. I'm just going to try re-importing it because that should not happen. Just kill that, open it again. Okay. And right, sorry about this. I did say it worked 50% of the time. So there's an error in my CMake configuration. So let me just have a look here. There's a space. I put a space in the path that I copied in. Fantastic. So I'll just go back into my Android configuration in the producer, and here's the culprit here. I mean, you'd think the producer could strip spaces, but hey. Right. So I'll just resave that. We should see that change there. I'll try resyncing. Fingers crossed. Right, so now we have a run configuration. Now, JUCE takes a while to build, but luckily I have actually thought of that, and I brought some pictures of my cat whilst it compiles. This is my cat Maverick. He likes to wear slippers, both mine and my wife's. He likes to sleep in my bed, and he sometimes thinks he's a baby. His favourite thing at the moment is he's got very needy in his old age, and so he likes to give you a hug, and the hug normally involves him putting both paws around your neck and then sinking his claws in. So you kind of have to just grimace and go, okay, when he's done, he's done. But yeah, so that's fun. So right, so the app has deployed. Again, we should hear the square wave when I tap on the screen. And that's a JUCE app running on Android pretty much straight out of the box, and the exact same latency, very low latency. So there we have it. So that's how to deploy both a kind of a native Android app and a JUCE app onto Android. Use the JUCE develop branch for producer, clone the Oboe repo and set the path at enable, and when you're building, just use a single ABI. Right, okay, last section. When you're working with audio synthesis, or in fact doing anything interesting with sound, you are going to run into audio glitches and things that don't sound right. So the next part of my talk is about identifying the cause of those glitches using a couple of tools. So, right, so I'm going to go back to the Audio Engine app that I developed earlier. And instead of using one square wave oscillator, I'm going to use 150. Now, this is a slightly contrived example. Like, I know I'm going to push the CPU over what it's capable of on this device deliberately so that we start getting underruns. But you know, you may not be so lucky. You may not know what the cause of your underruns are. But this, you know, just to illustrate what can happen. So I've got this oscillator here, which is a mega oscillator, which consists of 150 square waves. So I'm going to change my audio engine to use this new mega oscillator and include the header, please. Thank you. Right, so I'll just run this. Just kill the other apps, and you should be able to get an idea of what it sounds like. Okay, so here's what it sounds like. Now, did you hear that artifact at the start there? And if you can hear a few things in there. Like, it sounds okay, but there's a few, like, let me turn it up a little bit. So there's things that sound not quite right in there. So if I was developing this app and I didn't know that I was, you know, using a ridiculously large number of oscillators, my first thing that I would do would be to run a tool called systrace. So systrace is a command line tool that ships with the Android NDK, and it allows you to take a trace of the device for a specified amount of time, and it allows you to kind of see what's going on in the system during that time. So I specify the time, 5 seconds. I specify the package name of my app, the output file, so output's an HTML file, and these three are the most important, these are the categories of the system which I want to trace. So I'm using the audio subsystem, the CPU frequency, and the CPU scheduler are the things that I'm interested in. So I'm going to tap on the screen for 5 seconds, so it's producing data, and run a trace. So. Okay. So now if I just open the HTML file, and I will have to go back to Chrome, just give me a sec. Okay, so it's opened this trace here, and I can see, I mean, it's quite difficult to see probably, but I can see that I've got 4 cores, CPU cores, and I can delve into what's going on these cores during this 5-second trace. But what I'm actually interested in is this section here. So this section here, which these rows all start with AA, which stands for A audio, and that's the underlying audio API which is being used. Tell me the status of the audio subsystem. So this AA ready line shows me the status of the audio buffer. Now I can see here that it's running completely empty up until this point here. And if I actually click on it, it'll show me a large negative value. And that tells me that the buffer has underrun by an enormous amount. So I'm actually not supplying data into the audio buffer fast enough. And this is confirmed by this line here, AA underruns, which tells me the number of times which I've not supplied data in time inside my audio callback. and that'll be increasing over time. So I now know that it's not my DSP code that is, somehow creating some noise in the signal. It's actually the fact that I'm just taking too long to generate the data. But I can kind of confirm this and understand exactly what's going on inside my callback a bit better by running the profiler inside Android Studio. So I will do that now. So this is going to restart the app and attach the profiler to it. Or at least it should do. Just give me a sec. If you can hear noise, it's from the Mac. It makes an incredible amount of noise. Okay, so here's the profiler. And again, this gives us a real-time view of the Android system. So we have CPU, memory, network, and energy. And I can see real-time events. So if I tap on it, you can see at the top here, we've got touch events coming through. So it kind of shows me an overview of the system. If I click on CPU, I can see all the threads that are running on the system. And the thread that I'm interested in is my audio thread here. So if I click on this, and I'm going to run the same test. So I'm going to run for 5 seconds. I'm going to sample all the C++ functions which are called during this time. So okay. Let me just try and get rid of that noise. There we go. So down here, we've got all of the function calls that were made during this 5-second trace. The system calls are in blue, and my calls are in green. Now this is kind of useful, but there's so much data in there, it's difficult to understand what's going on. What I can do is I can use this flame chart, and that will aggregate all of the method calls and tell me how much in total time I spent in each one. So I can see here, if I look at oscillator render audio, I spent 4.84 seconds of my 5 seconds in this method, which is far, far too long. In fact, the top-down view will give me an even better look at that. So I spent 99.73% of my time in these audio callbacks, which is why I'm getting so many underruns. So what can I do about this? Well, the point of this talk is not to tell you how you can debug your code, but to really help you, give you the tools so you can pinpoint, hey, it's this line of code which is causing the problem. Now, in my case, the problem is fixed by adding compiler optimizations. So now if I rerun this with the -O fast compiler optimization, we should hear a nice kind of clean sound, no audio glitches, which is nice. Okay, right, back to this. So we can use systrace for understanding the audio subsystem. We can use the Android Studio Profiler. It's available in version 3.2 and above for method tracing and performance tuning. So I mentioned earlier that setting the minimum possible buffer size was a really bad idea. And there is a better idea, a better method that we can use for tuning the latency on a given device. So if I go back to Android Studio and into my audio engine, Oboe ships with an object called a Latency Tuner. And if I just create one of these, that takes my stream object, and it will automatically tune the buffer size so that I don't get any underruns. So every time it receives an underrun on the stream, it will increase the buffer size. So that's super useful, and this can be run very, very quickly on app startup, so you get the optimal buffer size for a given workload. You can also specify a maximum buffer size, and this is useful. Like, often you don't want to set a buffer size which is equivalent to, say, a second's worth of latency. Like, if you're writing a synthesizer app, if your latency goes over about 50 milliseconds, then it becomes very unresponsive and the user experience is terrible. So what you can do is you can set an upper bound for your buffer size, and if you're still getting underruns when you're at that upper bound, then you need to start thinking of other ways which you can scale back on your computational load. For example, reducing the number of voices, or reducing the complexity of your reverb algorithm, or other things like that. So probably a safe maximum would be, let's say, 4 times the burst size. That's, probably want to do a more complex calculation, but that'll do for now. Just create a new field, which is the latency tuner. And then every time I'm in my callback, I'm just going to call tuner.tune. And that's going to automatically tune my latency for me. And that's all you need to do to optimize your buffer size.
How do you know the value of get frame per burst, and how much is that roughly?
So it's dependent. The question is, how do you know the value of get frames per burst? And the answer is, it depends on the audio device. So it generally depends on the audio codec and how much memory is read in each DMA controller operation.
But like roughly, so it would be like.
So on this device, it would be 192 frames, or 96. I can't actually remember. Maybe 96, I think. Yeah, okay. So, right. So we've done latency tuning. And for the final bit, I just wanted to kind of illustrate that, I know a lot of you do desktop apps, but sometimes people forget that mobile has capabilities that desktop does not. And one of those capabilities is sensors. We've seen quite a lot to do with movement and using sensors. And so I thought it'd be fun to just show you how you can use the sensors on Android to control your audio engine. So, to do that, I'm back in Java land here, and I'm just going to set up my activity to listen to sensor events. So I load a sensor manager. I get the rotation vector sensor, which is will give me values on 3 axes to do with the rotation of the device. I listen for those events, and I tell the manager that I want the fastest possible updates. So to listen for these events, I just need to implement the sensor event listener. And I'm going to implement 2 methods on sensor change and on accuracy change. I don't care about the accuracy, but I do care about the sensor change event. So I'm going to change the frequency. So I'm going to do set frequency based on the x-axis. And I need to scale this value. So I'll just do 80 plus 60 times event values 0. And I will explain what that does. So I'm going to start with a base frequency of 80 hertz. And then I'm going to go to plus or minus 60 of that value, because the values on the x-axis will be between -1 and 1. So I'm also going to set the spread. So my mega oscillator is set up so that I can vary the spread of the oscillators within a given range. So I'll do 0.5 plus, actually I'll just do 0.5 times values 1. And this is the y-axis. So I just need to quickly implement these methods. Okay, so I'll just do osc set frequency, and I'll just do the same in here, gin set spread. Okay, I think that's everything. Let's run this. So what we should hear is the same kind of sound, but the pitch will vary as I rotate the device forward, and the spread will vary as I rotate the device left and right. There is a problem. That shouldn't be happening like that. Oh, I've got the axis the wrong way around. So, so as I rotate left, change the pitch, and the spread should change as I move forward and back. Anyway, so you can see how that's controlled. How long have I got? 7 minutes, fantastic. Right, who here has heard of the Amen break? Yes, my kind of crowd. So for those of you who have not heard of the Amen break is a 4-bar loop of a brilliant drum solo that was made by the Winstons in 1969 on a record called Amen Brother. It is the most sampled loop of all time. And it sounds like this. No, it doesn't sound like that. Why does it sound so horribly distorted? This is not doing the Winston brothers any justice at all. Okay, hang on. Right, I'll take that out. Let's try on that one. I have no idea why this is distorting. Maybe I'll just turn the volume down there. It's just a straight Mac output. Okay, well, let's give up with that. I was gonna like do a little performance of this over the top of the backing track, but I'm pretty sure you can get the idea. So, right. So if you want to check out the Oboe library, it's available on GitHub. There's like videos and tutorials and all sorts of good stuff. We'd love for you to use it, file bugs, and yeah, you can contact me directly over GitHub. That's it. Thank you all very much.
Just a very quick question. You open the stream, and then when you tap or you don't tap, you start or stop feeding data, but the stream is always on.
Correct.
There was you showed that we could return continue or stop at the provided callback.
Yep.
So why not stop and then restart? Is there an overhead or something like that?
Yeah, there's startup latency when you start a stream, normally in the order of tens of milliseconds. So you should always keep your stream running like throughout the lifetime. If you're ever thinking of producing audio, keep it running in the background. Although it consumes power, the latency cost of starting it is significant. So yeah, keep it running.
Hey, I've kind of observed that on some Android devices in like a live input scenario, it's necessary to keep the CPU kind of doing something, otherwise it'll drop the frequency, and when you play and input, it doesn't sort of ramp up quick enough. Does Oboe do anything to help with these kinds of situations?
So this is a very tricky topic. CPU frequency scaling is a problem that affects virtually all mobile devices because everyone cares about battery life. apart from people who want to do stuff in real-time audio, who only care about latency. And unfortunately, the frequency scaler doesn't change based on whether the device has power. So it will always basically be ramping down to try and conserve battery life. So there's no easy answer to this. In the past, I've advocated for a couple of things, one of which is really bad and one of which is like horrible. So the really bad thing is touch boost, which is where some OEMs will boost the CPU frequency based on whether or not there's touch input. So you can kind of, if you make the user hold down a button on the screen whilst they're recording, then you won't have that CPU frequency drop. I told you it was bad, right? The other thing you can do, which is horrible, is you can use ASM no-op operations to keep spinning. So keep your load high, but not necessarily doing any useful work. And then the scheduler thinks, oh, this app needs a load of computational bandwidth, so it keeps the CPU frequency high. So yes, you can do that. I've written a sample which does that, which is not on the Oboe repository, but it's on the high performance audio repository. If you just search for that, you'll find it. So, I mean, we're aware of it, and the OEMs are aware of it, so we're working on it. So
is it not something that affects Pixel devices, for example?
No, it does. It will affect pretty much all devices, and the solution is to essentially keep your load at a reasonable level so you don't get... The really key thing is not to scale back your load just because you're hitting a 100% of the CPU bandwidth, but to keep your load high, because then the CPU frequency scaler will bump you up eventually. So.
Yeah, I'd like to know, would you recommend to use Oboe always for any app, or would there be a reason to pass by and use the original API or the underlying API?
So Oboe is only useful for real-time audio. If you're streaming audio, you're creating a radio app or the next Spotify, just use the Java APIs because they're a lot simpler to maintain, and you don't need real-time performance. So there's that. Is there any other scenario? If you're a middleware provider and you want very, very low level control over like all the stream parameters and that kind of stuff, then maybe use Audio directly. But yeah, mostly we'd recommend using Oboe. Like JUCE uses Oboe now, so and there's a lot of other companies using Oboe. So I think this guy. Sorry.
Okay, so I was wondering about the method to get the frame per burst.
Yep.
So that would return what we know, what we're used to know from the OpenSL times as the native frame per buffer, right?
Yep, that's right.
And I'm wondering what...
It's actually slightly better than that because what used to happen historically was you'd only be able to get the frames per burst, the optimal buffer size for the built-in audio devices, as in the speaker and the headphone jack, always the same value. However, if you call get frames per burst, it will using Oboe, it will give you for the current audio device, which could be USB, it could be Bluetooth, it could be some other audio device, and it'll give you a dynamic value rather than a hard-coded system value.
Okay, yeah, you answered my question
Okay.
because that was my question. And also, what about the sample rate? It's the same, right? So the native sample rate could be. Should I expect the native sample rate return to be different according to the device?
Yep. So it can be different according to whether you're using, and probably will be different depending on whether you're using USB, Bluetooth, or the built-in device.
Okay, thank you.
Yeah, that's great. What I was wondering, when we're using the Oboe wrapper in JUCE, because you showed all the Oboe settings with this this automatic adaptation. Forgot the name of that thing. Is that setting exposed somehow if I use the JUCE Oboe wrapper, the audio I/O device? Is it probably? I mean, when you had this automatic
fallback back to using OpenSLES.
To use higher latencies in times of when the CPU is hitting underruns.
Oh, the tuner.
Yeah, the tuner. Yeah, that was the name. Thank you.
Right. That is not something that I've seen in JUCE so far, but it's like, as you saw, it's like 2 lines of code. So I can submit a pull request if that's something. I mean, it's probably something that would need to be implemented on a case-by-case basis. Sometimes you'd absolutely want to say, just give me the smallest possible latency. I don't care if I get the occasional underrun.
Somehow configurable, yeah, right.
Yeah, so I mean, I'll talk to the JUCE team, but it could be a checkbox to say use dynamic latency tuning.
Ah, okay, yeah, that sounds sensible. Yeah, great. Thank you.
Okay. Oh, question over here.
Just a short follow-up question on that. Can you, so does the tuner stay at the frequency that it finds eventually, or at the frame rate, the size of the frames per second, or does it go back down once it's found like an upper limit?
Good question. No, it only goes up at the moment. So we're working on a sample at the moment that will go up to a reasonable maximum and then periodically kind of bring it back down again. But at the moment, it's pretty basic. It will just scale up until the point it doesn't get any underruns.
Right. Thank you.